Page 39. So this was the definition here in definition 4.3. The definition of the derivative of a function f at the point A is the value of this limit. Okay, so it's the limit of the relative change in value of the function. So the change in value of the function is what you see in the numerator. F of x minus f of a. You think of a as being some fixed point, and we're taking the limit of this fraction as x approaches a. In the numerator, you have the actual change in value, f of x minus f of a. And on the bottom, it's divided by x minus a, is the difference between x and the fixed argument a. So you think of that as the relative change in value, the change in value of the function relative to the change in value of the argument. You're taking the limit of this quantity as x approaches a, and this is going to be the derivative, okay, which is a measure of the instantaneous rate of change of the function at the point A. Okay? If it's a positive number, the function is increasing. It's a negative number, the function is decreasing. Function is zero. If the derivative is zero, it means the function is kind of flat at that point. With these kind of interpretations, you can appreciate when you look at the geometry lying behind that definition. When you look at this quantity, if you take the limiting process out, if you just look at that relative change quantity, f of x minus f of a over x minus a, for 2 points x and a, that quantity is equal to the gradient of this green line that you see drawn across the graph of the function there, okay, which is joining the 2 points on the graph at the arguments a and x. And the gradient of that line is a measure of the difference in value of the function at those 2 points. But it's a relative measure. It's relative to how far away the arguments are. Okay? And as you let x approach a, so remember you think of the a as being some fixed point. As you let x approach a, okay, you're still talking about these green lines drawn across the graph. But in the limit, as x approaches a, it's approaching this limiting situation, where you just have the point A, and then you have the tangent line to the graph, okay? And this is this tangent line locally at the point A, so in a small neighborhood around the point A, this tangent line will only cross the graph, it'll just intersect the graph at that point, and its gradient, the gradient of it, which is going to be the limit of these gradients, f of x minus f of a over x minus a, the gradient of it is the measure of the instantaneous rate of change of the function. So, okay, any questions about that definition or anything you'd like me to clarify about it? Now, we looked at, so that's definition 4.3, and there's a few different types of notation, which we talked about, which we need to be familiar with for it. We did some examples, example 4.2 last time. Okay, better quickly finish this review. This is where we looked at particular functions, f and g. So f was the function k times x for some constant k. G was the function k times x squared. And just using algebraic manipulation, using the property of limits, we were able to actually evaluate those limits directly. Okay. We also had the notion of higher order derivatives, and this is where you iterate the differentiation procedure. So you take a derivative of a function, and then you take a derivative of the new function that you get. You take a derivative of a derivative, and so on. And in the notation, this is written as d2f dx squared, say, if you're differentiating a function f with respect to its variable x. So that's the derivative of the derivative df dx, or d cubed f dx cubed is the derivative of the second order derivative. And in the other notation, higher order derivative notation. So higher order derivatives notation. In the other, we can write f prime as we saw last time for the derivative df dx. F double prime will mean the second order derivative, df dx squared. And f, well, you could even, maybe at a stretch, you could write f triple prime, and that would be d cubed f dx cubed. Okay, so that's how you represent higher order derivatives in that alternative notation. Now, it'd be a bit ridiculous just sticking loads and loads of primes against the thing because it looks ugly on the page and you can't count them by just looking at them. So the notation is continued that if you put a number, but put it in round brackets above the function, well, that's going to indicate the fourth order derivative. Okay, and in general, f to the power of brackets n is just a piece of notation for the nth derivative, df dx. It's a bit ridiculous even to start putting 3 primes, I think. 1 prime or 2 primes. Okay. By normal conventions, f to the power n, if you didn't have the brackets there, that would, well, that could mean one of two things. It could either mean the function value of f raised to the power n, or it could mean the function f composed with itself n times. Both types of use are made of that. You'd have to investigate from the context of where it was being used what exactly was being meant. But when the superscript is put in brackets, it's normally referring to a derivative of a certain order. Now, next in the notes, after that page, you'll see there's two pages here showing various standard results about the derivative. So derivatives of standard functions, and then on the second half of the second page, some general properties of the derivative. These 2 pages are taken from the standard departmental mathematics formula handbook. This is the one that you have available to you in the summer exams. And so this lists a lot of standard functions and their derivatives and integrals. Okay, so you can refer to this when you're solving problems concerning calculus. Okay, some of these we'll come back to. I mean, we've already kind of proved a few cases of the first result. We'll come back to various of these and discuss them, the derivatives of trigonomic functions and so on, the sines and the cosines and that. But what I'd like to do today, what I'd like to focus on today, is some of these properties of the derivative. Okay, so this brings us on to page 43. So now you begin to spot a theme here, or to notice a theme which we've seen before. When we did convergence of sequences and convergence of series, we proved results about how convergence behaved with respect to adding series or sequences together. Okay, we saw that it behaved very well when you take a linear combination of a sequence. Its limit is the linear combination of the limits of the individual sequences. And we saw this when we looked at continuity as well and limiting value of functions, limiting values of functions. So we're always, it's a kind of common theme that you're always checking in each new concept you introduce concerning functions or sequences, so on. You're always checking, does it mesh well, does it agree well with the operations that you can do on those sequences or those functions. Okay? So we see that again here. We're talking about functions, so there are several important operations we can do with functions, namely take linear combinations of them. So you can take 2 functions g and h and form a new function f by taking a linear combination of them. Or you can take 2 functions g and h and you can multiply them together, multiply their values together. And that creates a new function f, which you think of as g multiplied by h. So the question is, does differentiation fit well with those? Well, the answer is yes, it does. And there are formulas here that tell you what the derivative of this new function f is in terms of the derivatives of the component functions, the ingredient functions, if you like. And just scanning forward down to the chain rule. The chain rule is very important because it's to do with this very important operation and a universal operation, not just in talking about real valued functions, but any kind of functions or operations, this idea of composition, running one function after another, applying one function to the results of another, combining them in that way. It's an incredibly fundamental operation. So we can compose functions on the real line, from the real numbers to the real numbers. You can compose those easily. We often do. And so the so-called chain rule is the property of how the derivative of a composition of 2 functions how that relates to the derivatives of the individual functions. Okay? So we'll be seeing that as well. Then there's a quotient rule, which you can kind of think is composed out of product rule and the chain rule, I think, a little bit. But the quotient rule deals with quotients. When you take two functions, u and v, say, and form a new function, y. Okay, so we're going to work our way through these. We're going to prove all of these at various times. I think today, at least, we'll see the proofs of the linearity result and the product rule. Okay, but let's just have a close look at their statements first and have a look at a few examples, and then we'll turn to look at their proofs. And the proofs will use that definition 4.3, the one I showed you at the beginning of today, the one that we discussed last time. It'll use that definition and the facts about limiting values of functions that we've already developed up to now. Okay, so it'll be a good kind of making good, efficient use of the theory that we've built up to this point. Okay? So let's look at the linearity. So this is saying that the operation or the process of differentiation is a linear one. That means if you form a new function f as a linear combination of two functions g and h, so f is alpha times g plus beta times h, then the derivative of f exactly matches that linear construction. It's alpha times the derivative of g plus beta times the derivative of h. Okay? Extremely nice, a nice property. The derivative exactly mirrors the way the function was constructed. Okay? Linearity is a very deep, important property throughout all of mathematics, and you'll see it come up again and again. And whenever something is linear, whenever an operation is linear, it means it's very, well, it's a very good aspect of a operation, because it allows it to be studied quite well. It allows the operation to be more or less completely understood. Now the product rule. Okay, the product rule mixes it up a little bit. It isn't quite so neat and tidy as the linearity result. So the product rule says when you've got a function f, which is two functions multiplied together, that the derivative of the function f, the new function f, is this combination of the derivatives of g and h. So it's the function g itself times the derivative of h plus, swapping the roles around, the function h itself times the derivative of g. Okay, what it is not, so like, maybe this kind of thought is so dangerous you shouldn't even write it down, but if f is g times h, the derivative of f with respect to x is not the derivative of g with respect to x times the derivative of h with respect to x. Danger. Now, but I do find people claiming that in some of the work they do every year. Some of I see them attack problems by saying, well, the derivative of this function is the product of the derivatives of g and h. So, let that be, don't fall into that trap of thinking. I mean, this is what you might hope. If you were going from the linearity result, the derivative of a sum is the sum of the derivatives, you might expect this naively at the start. You might expect the derivative of a product to be the product of the derivatives, but it ain't. Okay? So if you ever find yourself leaning towards that, give yourself a good kick and remind yourself that it's not true. It may by a fluke turn out to be true in certain specific circumstances, but almost by accident, I think. But it's just kind of, having seen it now, obliterate it from your minds and don't fall into the trap of thinking that it is true. Okay, so in example 4.3, we've got an application of the product rule. So this is using the product rule, but taking the results, using standard results from the table of derivatives. Okay. So you can see here we're faced with this function y, this expression y, which is made up out of the product of two functions. Okay, it's y depends on x, but it's very clearly the product of two different functions. One is the function x squared minus 1. The other one is the function sine of x. So we can differentiate each of those factors. Okay, the derivative of u of x is 2x, and that itself is using the linearity result. Because the derivative of x squared is 2x. The derivative of a constant minus 1 is 0. Okay, constants don't change. They never change, so their derivatives are 0. So you're seeing the application of linearity in getting the derivative of u. The derivative of v, okay, that we're taking from the table of derivatives. We haven't proved that yet or explained that really yet in this course, but we will return to that idea and explain it. But the derivative of the sine function is the cosine function. And then you just put these two together according to the product rule. So you take the original function u, which is x squared minus 1, you multiply it by the derivative of v, it's cosine of x, and you take the original function v, which was sine of x, and multiply it by the derivative of u, which is 2x. Okay? So that's an illustration of the way we use the product rule. There's another example here, y equals x times e to the power x. This is example 2. So this is where we have a function defined by this formula, x times the exponential of x. Well, that's very obviously, very clearly, it's a product of two different functions. You've got x on the one hand multiplied by this other function of x, e to the x. Okay. So using the product rule, we let this be our function u and this be our function v. Du dx is the constant 1. Okay, we proved that last time, that the derivative of just x on its own with respect to x is the constant 1. The exponential function has this special property that it is its own derivative. The derivative of the exponential is just the exponential function. So that's another result I'm taking from the tables. Okay. Again, we'll return to that and explain that in a bit more detail in due course. But just using this to illustrate the product rule, then we can obtain the derivative of our objective function y as, well, it's going to be x times e to the x. So I'm keeping the u part unchanged and multiplying it by the derivative of v. And now I'm going to keep the v part unchanged, which is, again, e to the x, and multiply it by the derivative of u, which is the constant 1. So, well, I won't bother putting down the factor of 1 multiplying that, because it's not going to change it. Okay. That's another illustration of using the product rule. Okay. So on the one hand, we see these as rules, instructions that we can follow. We can take kind of known results about derivatives of standard functions, and using these rules, we can then obtain the derivatives of functions that are built out of these standard functions, linear combinations and products of them. And when we come to it, looking at the chain rule, we'll be able to deal with compositions of these functions. Okay, but we don't just want to take these, you don't just want to believe these because I've told you they're true. We want to actually see the proofs of them and appreciate the mathematical arguments that justify these results. Okay, so that's what we're going to do now. And we'll have a look at the linearity result first. It's the more straightforward of the two. So here we're dealing with two kind of input functions, g and h. And we have f as a linear combination, alpha times g plus beta times h. Okay, where g and h are differentiable functions. It's not written in the statement, but That's implied. The differentiable functions, and alpha and beta are just two, the coefficients in the linear combination, they're just two real numbers. Okay. So what do we know? Well, we know that G and H are differentiable, okay? So i.e., we know that there exists a derivative, the derivative of G at A. Which kind of notation shall I use? I'll use this notation, G prime at A. This is the limit as x approaches A of G of x minus G of A over x minus A. And we also know that H is differentiable. So H is a derivative at A, and that's the limit as x approaches A of H of x minus H of A over x minus A. Just the same thing, just written with H in place of G. So that's what we know. That's what we're starting off with. We now want to prove the result. So what we want to find, so you can see this as proving the result, but also see it as kind of discovering the formula as well. We could follow this argument through even if we hadn't seen the statement of the theorem, and we could be discovering this result for ourselves. What is the derivative of f at A? Well, we know how to write that down because we've got the definition of it. The derivative of f at A is the limit as x approaches A of f of x minus f of A over x minus A. Okay, that's what it is. Okay. But now we need to know something about the function f in order to be sure that this limit exists. Okay. But what we know about the function f is that it's built out of the functions g and h as a linear combination of them. So we should bring that knowledge to bear here. So this is just the definition of the derivative. That's definition 4.3. So we substitute in this formula for f. F is alpha g plus beta h. So what we're looking at there is the limit as x approaches A. Now what is f of x? F of x is alpha of g of x plus beta of beta times h of x. Okay. That's what the function f is. It's a linear combination of g and h. Similarly, the function value f of A is alpha times g of A plus beta times h of A. And all of that is still divided by x minus A. Okay, well now we've got a kind of much bigger, more complicated expression. It's become a bit unclearer, a bit less clear. So it's a limit of this large numerator divided by the denominator x minus A. But you can see in here, we see g of x, h of x, we see g of A, h of A. But we already know something about limits involving those because we know that g and h are differentiable. And so this limit g of x minus g of A over x minus A, we know that has we know that limit exists, and it's exactly the derivative of g at A, and similarly for h. And we can kind of see those expressions lurking in here. So the idea now is to manipulate this to bring out these two expressions. Okay, you can see them hiding in here. So do kind of algebraic manipulation of this carefully, respecting the fact it's a fraction and doing the right thing, but try and tease out how these are both appearing in there. So we're not yet doing anything with the limiting process. So that's just staying on the outside. But we can rewrite this fraction. We can rewrite it as alpha times g of x minus g of A over x minus A, and plus beta times h of x minus h of A over x minus A. So it's important to appreciate how you can change it to that. Well, on the one hand, what was I doing? I was just moving the various bits in the numerator around. I just brought all the g's together beside each other, the g of x and the g of a, brought all the h of x and the h of a beside each other. And then you see there's a common factor in the alpha is multiplying g of x, but alpha is also multiplying g of a. And similarly with beta and the h. Beta is multiplying h of x, and beta is multiplying h of a. So then I've got a bunch of stuff added together in the numerator. Well, I know how to split apart fractions. Okay, if there's a sum or a difference or whatever in the numerator, you can split that into two separate fractions with the same denominators and the respective parts in the numerator. So you split apart one fraction involving the g's and the other fraction involving the h's. And these common factors we can remove those from the kind of inside of the fractions and put them outside. And that's the sensible way to manipulate this. Obviously, there'd be lots of other ways you could rewrite or re-express that fraction. But this is the thing to do because this brings out what we know. Yeah, we know what the limits of these quantities are. So here we see exactly those quantities. We see it's a linear combination of them. And now we're going to call upon facts we know about this guy, facts we know about the limiting operator, the limiting process. Here now we're taking a limit of a linear combination of these objects, these fractions. And we know that the limit of a linear combination is the linear combination of the limits. Okay, we proved it. Well, we proved that in the case of sequences, we proved that in the case of series, and we've certainly looked at it, seen it in the case of limiting values of functions. We've done it for continuity of functions. Okay, so we're very familiar with that. So this can be written as alpha times the limiting value of x times a, x approaches a of g of x minus g of a over x minus a. So that limit, then separately this limit. Beta times the limit as x approaches a of h of x minus h of a over x minus a. Of course, these all need the kind of caveat on them that, you know, this limit is equal to this combination of limits provided these limits exist. Obviously, if these individual limits I'm writing down here didn't exist, then that would be nonsense that I've written down there. But we know they do exist because we know that g and h are two differentiable functions. Okay, so these limits do exist and they have names. They are the derivatives of the functions g and h. So the justification for that step is important. So the justification for that step is the linearity of limits, of the limiting process. That's what allowed us to come to make that step. And then we're just using the fact that these limits exist and they're called g prime of a, the derivative of g at a, and h prime of a, the derivative of h at a. So from start to finish then is exactly the statement of the theorem. That result there, that the derivative of f at a is alpha times the derivative of g plus beta times the derivative of h. Okay, that's exactly what is stated up there in the statement of theorem 4.5. Okay, so we can say this proves theorem 4.5. Okay, but so it's a nice example of taking the definition of this concept, the derivative of the function, applying it, using the conditions of the theorem, the fact that g and h are differentiable, and using what we already know about the properties of the limiting process. So we know that linearity is true. Okay, so the next one we should come on to then is the product rule. So this time we have f being g times h. The same setup information from before. I won't bother writing it down again, but we've got the same setup information that the derivative of g and the derivative of h exist, and they're given by those limits. So we have that information to hand. So we're going to prove this result in the same, roughly the same overall route. We're going to ask what's the derivative of f at a. Well, it's exactly, according to the definition, it's this limit. Okay, but of course now f has a different definition to what it had before. Now it's the product of the two functions. It's g times h. So this limit now is g of x times h of x minus g of a times h of a, all over x minus a.